Okay, it's 7:30 and we're going to get started. Welcome to the January meeting of the Johnson Space Center Astronomical Society. I'm Doug Holland, the president of the JSC AS, and this is our agenda for this evening. First, we're going to have an update on the C.L.E.V.E.R. Planets Project with Dr. Andrea Isella from Rice University. Then we'll have a members minute with Chris Wells and Treavor Quinn on the conjunction images. This is a Saturn and Jupiter conjunction. Then I'll be doing a members minute on M1, and we'll wrap it up with Star Party News with David Haviland. If you have questions or comments during our meeting, you can submit them either as a YouTube comment in the YouTube chat area, or you can submit them as an email at jscaslive@gmail.com as shown at the bottom of the screen. So first up is our main speaker. And first I'd like to tell you a little bit about Dr. Isella. Andrea was born in Italy, where he also received his education. He obtained a BS in astronomy from the University of Padua and a PhD in physics, astrophysics, and applied physics from the University of Milan. After that, he moved to Caltech in Pasadena, California as a NASA Michelson postdoctorate fellow. During that period, he worked on the construction of the Combined Array for Research in Millimeter Wave Astronomy, CARMA or CARMA, a radio interferometer located in the Owens Valley and capable of observing the sky at wavelengths between 1 and 3 millimeters. In 2014, Andrea moved to Rice University as assistant professor in the Department of Physics and Astronomy. And in 2020, he was promoted to the rank of associate professor in the same department. Andrea's main field of research is the study of star and planet formation. In particular, Andrea uses radio interferometers to image circumstellar disks around newborn stars to understand how planets are assembled. Andrea is also leading the construction of a radio telescope operating at very low frequencies, 10 to 80 megahertz, that will be capable of detecting aurora happening on nearby exoplanets, but that is a story for another day. Andrea has authored more than 100 scientific articles published on astronomical peer-reviewed journals and is the principal investigator of several projects funded by NASA and the National Science Foundation, including the C.L.E.V.E.R. Planet Project, which is the topic of today's presentation. Finally, Andrea serves as chair of the Next Generation Very Large Array Science Advisory Council and has received the 2016 the Young Investigators Award in Astrophysics from the Italian Scientists of North America Foundation. Last but not least, before becoming a professional astronomer, Andrea was a devoted amateur astronomer. He bought his first and only personal telescope, an 8-inch Celestron, at the age of 18 and helped creating an astronomical club in his birth town in Italy. The same very telescope now sits in his garage in Houston. Andrea enjoys using it to show stars and planets to his 3 small children and his wife whenever possible. With that, I'd like to turn it over to Andrea Isella.
Okay, can you hear me?
You're good to go.
Yes, thank you. Thank you, Doug, for the introduction, and thank you for inviting me to talk to you and to your meeting tonight. And yes, I have my telescope in my backyard. Fortunately, Houston is not the best place to look at stars at night, but once in a while, I'll take it out. And for example, recently with the conjunction of Jupiter and Saturn. But let's get to the point. So tonight, I would like to talk to you a little bit about this project. It's called C.L.E.V.E.R. project at Rice University, and in particular, I will tell you a little bit about what we are doing to understand how planets form. Okay. If you want to know a little bit more about what I do, there is here a link in my planetformation.rice.edu that you can click and see my webpage. So, what is this C.L.E.V.E.R. Planets project? So, a few years ago, myself and some of my other collaborators at Rice University, both in the physics and astronomy department and also in the department of Earth environmental and planetary science, decided to put together a very ambitious project with the goal of understanding how do you form a planet like Earth. And if you stop and think about what it entails to form a planet like Earth, you may realize that there are many steps. And this is very ambitious because it's really difficult from first principle to understand formation of a planet like Earth. So this slide here shows you 5 of the main steps that you need to go through in order to have a planet where you can live, right? At the very beginning here, you need to be able to understand how a planet in general form of the material out of which also form stars, so what is called interstellar material. And that will be the main topic of my talk. And essentially it's the only topic of my talk. And then there are other themes, 2, 3, and 4, 5, which are other steps you have to go through. For example, there is a phase when our solar system was very young and the Earth was very young, where there were a lot of impacts. So the solar system was populated by a lot of asteroids, or what we call planetary embryos. So the core of planets, and there were many of them, and they were colliding very often. And somehow Earth survived through that process and maybe even formed by collision. For example, we know that the moon, the leading theory for the formation of the moon is that there was an impact between Earth and another object, and this impact led to the formation of our own moon. So once the solar system became a bit older and a bit quieter, then you have to deal with the Earth itself. When planets form, they are very hot. They are most of the planet itself is melted, right? It's a magma planet. And so you may ask yourself, how do you get life begin on such a very weird and dangerous place, right? Imagine if the Earth was covered by lava, essentially. That's what you have. So, and the other thing is that in order for life to develop, you need some chemical ingredient. You need water, you need nitrogen, you need sulfur, and you need carbon and other things. And first of all, you need to have this ingredient on your planet. Okay. Second of all, you need to have this ingredient available on the surface of the planet, because imagine you form a planet like Earth, but somehow all the water goes underground in the core of Earth. Then there will, and the surface is dry. Then it will be very difficult to have life developing on Earth. So that's why there is a lot of geology to study if you want to study the formation of a planet like Earth when it was very young. So in this ambitious project, and that's why there is also collaboration between astronomy and geology, you need to include the geology, for example, how material gets sequestered in the core of a planet. If, let's say, the water goes underground, it's not the end of the story, because through, for example, volcanoes, you can return the Earth, you can return the water in the atmosphere. Okay, so there are many complicated projects, and this makes this project extremely challenging and indeed ambitious. Okay, so we are about halfway through this project. This was founded by NASA, and we are and it's a 5-year project, and we're not going to solve all this problem in 5 years, but it's a starting point. And so today I'm not going to go in detail of all of this point, because this will take many hours. What I'm going to do is to talk what I do in this project, which is essentially the very first part. Okay, and the 2 questions I'm trying to answer using astronomical observation are: the first is where, when, and how do planets form? And when I say planets, I mean any planet. They can be a rocky planet like Earth, but also Jupiter. And you may think that we know everything about the solar system and we know exactly how the solar system formed, but that's really not the case, right? We still don't really know well how the planets are around the sun form. Another question is that I'm actually not going to talk about much today. I'm going to stick to the first question. But another important question is, what is the abundance of life's essential ingredients where planets form? And this goes back to the fact that if you want to have a planet like Earth with, let's say, water, okay? And the idea is that without water, life cannot really develop. You need somehow bring water on Earth, right? The water today, the water doesn't form easily on Earth. All the water we have on Earth, in the oceans, in the lakes, in the snow, was formed in the interstellar space and was delivered to Earth either when the Earth formed or after the formation of Earth. And even today, we still don't know where the water on Earth comes. We think may comes from comets, but this is a theory, and in the last few years, this theory has been put under some stress, right? So we don't know if the water is primordial on Earth or comes later. Okay, so these are the kind of questions we want to study. Okay, when, where, and how do planets form, and what is the chemical composition? Is the chemical composition of this planet good enough to allow life to develop, or why, for example, Earth is habitable and Venus is not habitable? Okay, they are very close. What is the difference? Why one ended up a beautiful planet and the other ended up a very poisonous planet? So these are the overall questions you should keep in mind as I go through my presentation. And please, unfortunately, we cannot interact directly, but if you have questions, please submit your question. I'll do my best to answer them. So this brings me to the outline of my talk. I want to review a little bit what we know about planets outside the solar system, because that has been one of the main discoveries in the last 20 years in astronomy. And this will motivate also why we want to understand how these planets form, both the solar system and all the planets outside the solar system. And if I have time, I would like to talk to you a little bit about a project for the future to build a new telescope that might unveil the formation of planets like our own Earth. Because as I will show you, we can study formation of planets maybe like Jupiter, but we still don't have telescopes that are good enough to study formation of planets like Earth. So let's start from the beginning here, just in order that we are all on the same page. So you might know, I'm sure you do, that in the last 25 years, we have discovered planets around other stars. And now we have thousands of planets around stars, and we have discovered so many planets that now we believe that on average, every star in the universe has at least one planet, probably more. So how do we go about discovering planets around stars? There are four main techniques that are shown in this animation. The oldest one, let's say, is radial velocity, okay, down here. So radial velocity works in this way. You have a star and you have a planet. The planet is too small and too dim to be directly observed with the telescope. But you use a trick that is given you by physics, which is the Doppler effect. So what is the Doppler effect? So instead of looking at the planet, you look at the star. And the spectrum of the star, so the lights that come out of the star, has some emission line or absorption line in this case, which are these black vertical line. So as the planet orbit around the stars also orbit a little bit about the planet. So they both orbit around the common center of mass, which means that the star wiggles back and forth. And this wiggling of the star creates a shifting wavelength in the spectrum of the star. So we cannot see the planet directly, but we can see this weird behavior of the star, very peculiar behavior. And then we can tell that if the star behaves in this way, is because there is a companion. The amount of shift in wavelength tell us about the mass and of this companion, so we can tell whether the companion is a star or a planet. Okay, it's a very powerful technique. We can use another very powerful technique, which is called planet transit. This works a slightly different way. So this is actually a real movie of the sun. And pardon me, I think this is Mercury. I don't remember if this is Mercury. This thing is Mercury passing on top of a disk of the sun. So what you do, you take a telescope, you look at your star, and you measure how much light you receive from the star. And stars are generally maybe variable a little bit, but generally stable. So you have a stable amount of light. If there is a planet that passes in front of the light, the planet obscures a little bit of the stellar light, And so you can see in this plot, as the planet is in front of the star, the stellar light dims by a tiny amount. And as the planet moves away, so you see the planet is moving in front of the star, it dims a little bit. And then as the planet moves away, the stellar light goes back to the original value, okay? So if you can do it, but the dim, I'm sure you cannot read the label here, but this star is dimming by 8%, okay? Sorry, this is 0.08%, okay? So very, very minuscule dimming of the light. But if you have a good telescope, you can measure that, right? So transit tells you about the size of the planet. The bigger is the planet, the deeper will be the dimming, okay? So they don't tell you the mass, they don't tell you where they are, so they don't tell you the orbital radius, but they tell you the size. So if you can combine the transit and radial velocity, the radial velocity tells you the mass, planet transit tells you the size. So if you combine these two, you can get mass and size, which means that you can derive the density of the planets. I don't want to spend much time on microlensing. This is another technique that use effect due to general relativity, which is the lensing of light, but let me skip that. Can be used only in very peculiar cases. The most easy technique to understand to detect planet is direct imaging. Direct imaging is simply, you take a telescope, you take a picture of your star, and if there is a planet, it shows up as a point of light close to the star. This is easier to say than to do because stars can be 1 million times more luminous than the planet. And so the star will outshine any planet around it. So you need to use very smart technique to remove the stellar light. And indeed, in this picture, the stellar light is this weird structure because it's being removed. And only when you remove the stellar light, you can see these dim planets showing up, okay? So this can be used only if these planets are very bright and very far away from the central star. So these techniques have been really improved a lot in the last 20 years, okay? 1988, we go back some few years here, 1988, these were the only planet we knew were Earth, Jupiter, Neptune, Uranus, Mercury, Venus, and Pluto. Right? Only the planet in the solar system. Now, Pluto is not a planet anymore, but that doesn't matter. So, and people were speculating that, yes, there are planets around other stars. Thanks to radial velocity and transit technique, starting from 1988, you see that as time goes on in this animation, all these dots are planets that we discover around other stars. And these on the vertical axis show the mass of this planet in Earth masses, okay, where 10 to the 0 is 1, Earth is here. The horizontal axis is the distance from the star, so Earth is at 1 astronomical unit, okay, so Earth is here, 1 astronomical unit, 1 Earth mass. Jupiter is 5 astronomical unit, about 300 times the mass of Earth and the other planets, okay? And you can see that the planet we discovered are weird objects, okay? The first planet discovered where this bunch of planets appear on the top left. These are called hot Jupiter because they are as massive as Jupiter. You see they sit on the same line here, but they are incredibly close to the Ross star. Jupiter is 5 AU. These planets sit as a fraction of AU. It's like having a Jupiter, you replace Mercury with Jupiter, and it's not even that close. Mercury would be something like here. Okay, so much closer than Mercury and as big or much bigger than Jupiter. So they are called hot Jupiter because they are so close to the star that they are very hot. There is another group of planets which are more like the classical Jupiters, right? Giant planet, gas giant, far away from the star. And then there is this interesting family of planets here. So they have a mass. You see Earth is here, Neptune is here. They have a mass between Earth and Neptune. So between something like 1 times the mass of Earth and maybe 10 times. But they orbit very close to the star, about where Mercury is or even closer. Okay, these are called sometimes super Earth or mini Neptune, just because they are in between. Okay, but in the solar system, we don't have, it's interesting that This seems to be the most common planet in the universe, or Jupiter and super-Earth, and we don't have anything like that in our own solar system. I should say that you see there is this wedge down here on the right, with this color in blue. So this region is empty. And the fact that it's empty is not because there are no planets there, because if you have the planets in this region, we cannot see them with our telescope. They are too dim or too far away from the star to really be observable. Okay, so keep in mind that the fact that this region of this figure is empty is due to our incapability to look at these planets, not because they are not there. We think there are maybe many planets here. It's just they are very difficult to observe. You may remember that in 2009 there was a Nobel Prize for Physics was awarded for the discovery of exoplanet. So after the discovery, and it was awarded to the people. There is one cosmologist in the group, which is this guy. This is Didier Queloz and Michel Mayor. They were the two astronomers that discovered the first hot Jupiter around 51 Pegasi, so 51 Pegasi b. Okay, so what I want you to take home from this picture is that planets in the universe, or planetary system in the universe, can be extremely different from the solar system. Another way to show it is in this very colorful picture. Okay, this is a quite busy plot. So each object here is a planetary system. Up here is the solar system. Only the giant planets are shown, so Jupiter, Saturn, and Neptune. And these are all other planetary systems we have discovered. And the size show you the size of the planets. Okay, the bigger is the dot, and the bigger is the planet. And there are weird systems. There are this system where many planets. Most of them are very, very small, as you can see. Right, this planet orbit very close to the star, and this is due to the fact that we can only see planets if they are very close to the star. Okay, but there are very weird systems here. There are systems with 6 planets orbiting within the orbit of Mercury. How do you get something like that? Okay, it's very difficult to understand. So what I'm trying to do with my study is try to understand how you can get planetary systems that are so diverse. Okay, what is the reason why you don't always get the same configuration? Right, they are all different. What is causing them to be so different one from the other? How do you answer the question? Well, there are two. Let me go back 1 second here. There are 2 possible explanations for this big diversity. Okay. The first explanation is that they were born differently. Okay. Some planetary systems are born in one way, other in another way. Another explanation is that maybe they are born in a similar way. They were born in a similar way, but they evolved differently. So this slide, the title is "Nature versus Nurture," meaning were they born in different ways, or did they evolve in different ways? And how do you go about answering that question? Well, you can use these other figures. These other figures show again each circle is a planet, but now instead of showing you the mass and the distance from the star, on the vertical axis, this is the distance from the star, so the orbital distance of the planet, 1 astronomical unit, 10, 100, 1000, and this is a log scale. And on the horizontal axis now is the age of the system. Okay, so the solar system is 4.5 billion years old. So you see these 2 lines here, these 2 blue lines. This is 1 astronomical unit. The vertical line is at 4.5 billion years. So Earth is here. Okay, and you can see that the vast majority of planets we have discovered so far are around old stars, like the Sun, older than about 1 billion years. There are very few objects that we know around very young stars. If you want to understand how planets are formed, you want to try to discover planets when they are very young. Because you don't know, for example, because during the evolution, planets can move. Planets can form very close to the star and move out, or can form farther away from the star and move in. And the location where planets form is very important because, for example, in terms of water, if planets form very close to the star, they might not have any water because they are too hot to have water. If the planet form farther away, they may have a lot of water in form of water ice. So the location where planets form is very important to understand the chemical composition of planets. So we are going to talk about these very young planets that are very difficult to see. The reason why there are few dots here is because these observations are very difficult to do, and I'll show you why is that. Okay, so how can we study where and how planets form? I think this figure motivates why we want to fill this figure on this side, on the left side, so that we can try to understand how planets evolve and planetary systems evolve. So how do we study planet formation? Well, first of all, you want to look where planets are forming nowadays, or stars. So planets form around stars, when both planets and stars are very young. And in the solar neighborhood, so in the surrounding of the sun, there are regions where stars and planets are forming nowadays. This is a beautiful image that many of you, I'm sure, recognize. This is a beautiful Orion Nebula, M42. And this is what you are seeing here. All these colorful images are gas and dust. That is what we call a molecular cloud. So the stars and planets forming molecular cloud, where you have big cloud of gas and dust that collapse, and out of this collapse you get a star. Indeed, if you zoom in this picture using the Hubble Space Telescope, you see things like this. Okay, what this interesting object looks like a tadpole. The white stuff at the center is not the yolk of an egg, but is a baby star. And this baby star is surrounded by this dark stuff here, which is a circumstellar disk. So it's a disk made of gas and dust. And everything is embedded in this cocoon that is brighter on one side because it's illuminated by the star in the trapezium. And there is this weird, interesting tail that we still don't understand exactly how it forms. So this is a baby star, and the baby star is surrounded by a disk where we think planet form. The analogy is with human life, right? This is the analog of a newborn. So if you want to understand how humans come to life, you don't go study a population of elderly people, right? You go and try to find a pregnant woman and study how is the birth of a baby. The same for star. If you want to understand how planets form, you don't go look around planet or a star like the sun that are very old, but you want to look around these baby stars. So this is a sketch of how we think the planet formation happens. So you start from a big cloud of gas. Gravity tends to pull things together, but if this material rotates a little bit, what you form is a star at the center, and the conservation of the angular momentum leads to the formation of a rotating disk through processes that we don't understand, and that's what we are trying to study. Planets form. Okay, these disks are made of gas and dust. Somehow they stick together and they form planets. What we know is that this process takes a few million years. So remember, the solar system is 4.5 billion years with the B, okay? And this process takes about 1 to 5 million years, okay, with the M, okay? 1,000 times less than the age of the star. Eventually, the material around the star dissipates, either because it's accreted on the planet or because it's dispersed, and you're left with a solar system like our own, a planetary system like our own solar system. So after about 10 million years, your planets are formed. And then they can evolve, they can gravitationally attract each other, they can evolve through what we call gravitational scattering, but most of the initial evolution is done, okay? So going back to the same figure I showed you before, this again shows you planet, the horizontal axis is the age of the star, and the vertical axis is the distance from the star. By the way, the size of these dots is the mass of the planet. So this region here that I highlighted in pink is where planet formation ends. So if you want another way to see it, if you are on the far side, far left of the image here, there are no planets. They form in this period. When you get in this pink region, formation ends because there is no material left around the star. The reservoir material are gone. And after these about 10 to 100 million years, then they evolve, okay? And we don't know how they evolve, okay? So let me tell you a little bit now about these materials, the womb from which planets form. So when stars are born, they are surrounded by this material in a disk. It's like a donut, right? Imagine you have a donut. There is a hole. In the center of the donut hole, you put a star. The donut is this material that rotates. However, it's a very flat donut. Donuts are pretty fake. Disks are very flat, okay, because gravity pulls things toward the midplane, okay? The material rotates, and so they pull things toward the midplanes. So these donuts are very flat, and they have a lot of gas and dust, so they are very dense. And the fact they are very dense means they are very opaque to optical light. So if you try to look at the optical light, you cannot see what's going on in the center of this disk, because it's like trying to look through a cloud of dust particles, right? I mean, when there is a dust storm, you cannot see through it. You cannot even see it through normal clouds, right? So the hidden part is hidden if you look in the visible light. Okay. However, if instead of using visible light, you go to longer wavelength, infrared, but more importantly to radio wavelength, then they become transparent. So radio wavelength allow you to see through this cloud and see what's going on in the very center of this disk, where we think planets are forming. Okay. So these are two pictures of a real protoplanetary disk. And to show you that there is this effect due to the wavelength, the left side is an image taken in the infrared at 1.6 micron. And on the right side is an image taken in the millimeter wavelength, 1.2 millimeter. Okay, and so in the infrared, you see the surface. So let me go back here. See this yellow, what I show in yellow is the surface of the disk that you can see if you look in the infrared light. Okay, so in the infrared, because you are so opaque, you can only see the surface. However, when you go to the millimeter, you see the midplane, and you can see the geometry very well. It's like these disks are like, I told you that it looks like donuts. The better analogy is like a bowl, right? They like you have two bowls. So this is the top side, and you can see the bottom side a little bit here. But the midplane, the middle is very opaque in the infrared. When you go in the millimeter, they are very flat, okay? Because now you see only the midplane layer, very flat, okay? And we'll go back to this observation later. So there are a lot of things happening. So I told you planets form in these disks. Planet formation must be done, at least giant planet formation like Jupiter, must be done in a few million years, because after that there is nothing left, okay, to form your planets. A lot of these disks are made of dust particles. When I talk about dust particles, you can imagine everything between like the sand in the beach to the pebbles to really fine dust, okay? Not much different from the dust bunnies that you find under your bed. Okay, and there is a lot of gas, however. Most of the mass in the disk is gas. And when I say gas, I mean hydrogen, helium, but there are also molecules. So for things like carbon monoxide, water, ammonia, and all the molecules, simple molecules you can think about. And there are a lot of interesting things happening. This stuff on the left, don't pay particular attention. It's just to highlight some physical processes. The dust particles collide. When they collide, they can stick together, or they can bounce, or they can break apart, fragment. There is friction between gas and dust particles. The large dust particle tend to settle toward the midplane. So you have the sedimentation process. And in some way that we still don't fully understand, out of this which brew here, you get planets, okay? How that happen is what we are trying to understand. So, but it's a very difficult task to get something like Earth, let alone Jupiter, when you have to start from something like this on this figure. So in the top left, this is your initial. It's like you're playing with Lego. You want to build a planet, and your Lego block are this one on the top left. Okay, your Lego block are 1 micron in size, and you want to build something that is thousands of kilometers out of Lego blocks that are 1 micron in size. So good luck with that. But somehow nature finds a way to do that, right? And you need to go through many steps. And so you get these tiny particles, micron size, then they grow in size, they stick. There are van der Waals force, electrostatic force that can attract these particles, they can stick together, and you can get to kind of sand particles. And then here is much more difficult to understand what happens. They keep growing, you can get things like pebbles that are millimeter, centimeter in size. And then we are kind of lost, because how you go from pebbles to objects that are very big, we don't understand, right? Because as your experience, you should tell you, if you throw 2 pebbles, if you collide 2 pebbles or 2 boulders, they don't really stick together, right? They bounce and fragment. When they get very large, up here, let's say 1 kilometer or 10 kilometers, then they are so big that the gravity of these objects is sufficient to attract other objects. So if you can somehow get to this point, then it's easy to go all the way to Earth, easier, because then the gravity helps you. But in this regime between, say, pebble size and small asteroids, we really don't know what is the process that allow you to bridge this gap. Okay, so this is a very active field of research. So I told you that there are also, these disks are made of dust, gas, and there are also molecules. And and one important thing is to understand, if you want to understand the chemistry of planets, whether one planet may be suitable to life, you want to know, for example, if there is enough water, if there is enough oxygen. And so using radio astronomical observation, we can look for molecules, because molecules, they rotate, and what they do, they emit light at millimeter and submillimeter wavelength spectral lines. And indeed, we have detected a lot of molecules in this protoplanetary disk. This is some very simple molecule like carbon monoxide, little bit more complicated like water, where you have 3 atoms, 4, 5, and 6 atoms. But by mapping the distribution of these atoms throughout the disk, we can try to understand what is the ingredient out of which planet form. But I'm not going to talk much about that. I'm going to talk mostly about, essentially it's only about the dust, these solid particles that form the core of planets like Earth, or the core of planet like Jupiter. Okay, so now that you know a little bit about what we think planets form, the question is, can we see these newborn planets? Show you the plot that most of the planets we have discovered so far are around old star. Now the question is, can we see planets around young star, right? It's right after they were born. And this is much more difficult, because you have this disk, right? So these young stars are surrounded by this thick disk of gas and dust. If you have a planet in this disk, you cannot use pretty much any of the techniques I told you that are very nice to detect planets around old star. But if you have a planet in this thick disk, planet transit doesn't work, because you don't see this. If you have if in order to see a planet transit, you need to be in the orbital plane of the planet. But if you are in the plane of the disk, what you see, you don't even see the star, because there is a disk, like there's a picture of what you call an edge on disk, right? Imagine you're sitting in the plane of the disk, you don't even see the star, because the star is completely obscure. So planet transit is a no-no. Can we use radial velocity? So looking at the wobble of the star. Well, there is a lot of stuff around the star, so the star will wobble even if there are no planets. And young stars are very active. They are like small kids. They jump around all the time. And stellar activity in young star can mimic planets even if they are not there. So radial velocity is another very difficult technique to use. So we can use direct imaging to some extent, but that's what you see, right? In infrared, you see a big disk. If there is a planet in the disk, it's hopeless. You're not going to be able to see it. However, if the planet is big enough and has cleared the disk, like in this case that I'll show you later, then we can see it. So if these three techniques, which are the easiest one to use and the one that have been used to detect planets around other stars cannot be used, what do? Do we give up? No, we don't give up. We try something else. And there is another technique that I'm going to talk to you a little bit. It's called planet-disk interaction. So what is this planet-disk interaction business? Okay, so I'm going to show you a animation, which is a numerical simulation. These are not observations. This is produced in a computer. This circle, this color circle, is a disk seen from the top. The color tells you how much gas you have. Black is very dense, and you go down. As you move away from the star, you have less and less material. Imagine when the solar system was very young, it was something like that. And then what I do, we put a planet here at 50 in the 50 AU in the simulation. Doesn't matter the scale. Okay, a planet like Jupiter. And now I'm going to start the movie and see what Jupiter does to the disk. Okay, now it's very smooth. If I run my simulation, so the planet does not rotate in this video because the camera is fixed on the planet. Okay, but in reality, the planet will rotate around the star. So see what this planet does. So the interaction, the gravitational interaction between Jupiter and the disk produces a torque, a tide, and this tide pushes material away from the planet, and it opens up a large ring, this white ring, which is a gap, is a circular gap where there is essentially no material left, because the material that was here is being pushed away. And then it creates other stuff like these blue spiral arms. So if there is a planet in the disk, in this very young disk, maybe we cannot see the planet itself because it's extremely dim and small. But if we see this big structure, like these big rings, that this big ring will give away the presence of the planet. And by studying these rings, we can infer the radius, the orbital radius of the planet and the mass of the planet. The more massive is the planet, the larger will be these gaps. And just by measuring the radius of these circular gaps, we can infer the orbital radius of the planet. And this will be clear in a few slides. So you may say, well, how do you know that this is actually how nature works? This is maybe a theory. How do you know that's true? Well, we knew that this theory was born to study and explain the ring of Saturn. And this is Saturn, the beautiful rings, Saturn Aurora. I'm not going to talk about that, although it's another interesting topic. And Saturn rings, you see there are these divisions, this black circle, which are divisions, right? And there are many of them. The biggest one is called the Cassini division. And so now Saturn rings are very different from the circumstellar disk I'm talking about, because in my circumstellar disk there is a lot of gas. Saturn ring, there is only dust particles, but the physics is the same. So what are these divisions? Why there are divisions here? Why there are these gaps in the Saturn rings? Well, there are gaps because there are moons that, through the same process that I just described, the tide between the moon and the disk pushes away material and opens gaps in the Saturn rings. Okay, this is a beautiful picture from the Cassini probe, and this is this Saturn moon pan inside the Encke gap in the A region. Okay, so the same process. Imagine that in this picture, can you see the moon pan? No. But you can see the division, right? Yes. So if you know that this process works, from this division, you can infer the position and the mass of the moon. And that's what the trick we are using for in protoplanetary disks, okay? So how do we observe protoplanetary disks? So Saturn is big and is close to us, so we can send the probe. What do we do with protoplanetary disk? So first of all, protoplanetary disk, I call protoplanetary disk, I also use the term circumstellar disk. These two terms are the same, essentially. They are very small. So you need to have very big telescopes. To show you an analogy, this is a Rice football stadium. This is the moon. The size of a planetary disk is equivalent of having the Rice football stadium on the moon. So imagine you want to watch a football game that is happening on Rice football stadium that is now on the moon, and you're sitting in your backyard. Okay, the size, the telescope that you will need to look at the football game is equivalent to the telescope that you need to look at this protoplanetary disk. Okay, so the nearest protoplanetary disk are about 3 times smaller than the full moon. So how do we observe them? So we need a very big telescope. The bigger is the telescope, the sharper is the images that it can give you. Not only that, you need a radio telescope, remember, because in the optical you're not going to be able to see much. So you need a big radio telescope, okay? So big that if you do the calculation, you need your telescope to be 15 kilometers in diameter. So now you cannot build an antenna that is 15 kilometers in diameter, as you can imagine, right? The poor Arecibo was few hundred meters. The biggest radio telescope on the world, single dish, is the fastest telescope in China, is 500 meters. So we can do few hundred meters, but not tens of kilometers, right? So how do we do that? We give up again? No, we never give up. So we find a way, and the way is called interferometer. So instead of using a big telescope, a telescope is big, 15 kilometers in diameter, we use many small telescopes, not very small, like this one. This radio telescope look like your satellite dishes, right? They don't need to be shiny, but these are telescopes. And this is 12 meters in diameter, so it's not that small. Okay, it's huge actually. And you build many of them, and you spread them out on a region that is across an area that is your 16, 20 kilometers in diameter. And now you point all your telescope toward the object you want to observe. You combine the signal using very complicated procedures, and you end up having a picture that's like having a telescope that is 16 kilometers in diameter. But now you do this trick using interferometer, and you lose something. It's not that you gain, it's not exactly the same. You lose something, but you get beautiful images. So now I'm going to show you some of these images. So using this particular telescope here is called the Atacama Large Millimeter Array. It's located in South America, in Chile. The reason is that you want to put it as high as possible above the sea level, because you don't want water from the atmosphere to interfere. Water absorbs radiation, radio wavelength. You want to get rid of as much water as you can. You want to be in the driest place on Earth, and the driest place on Earth is the Atacama Desert in Chile. So it's 5,000 meters above the sea level. There are 64 telescopes, 12 meters in diameter. And the sharpness, so the angular resolution of the images, you can get is milli-arc second. If you're not familiar with angles, if you have this telescope, you will be able to take a picture of a cent, of a penny, at a distance of 5 miles. Okay, so you get very, very sharp images. So let me show you, let me get to the point here. Let me show you some of the images of this baby planetary system. The first one we obtained in 2015. So on the left side here, there's an image taken in the optical, a lot of dust and gas, a young star here, but in the optical you are obscured, you cannot see what's going on in the center. You put your radio telescope and that's what you get out. At the very center, there is a star that you don't see at radio wavelength, because stars are very faint, which is another advantage of going to radio wavelength. You don't have to deal with the star, right? Star is not a problem. And you see a lot of rings. So the color is the intensity, okay? The yellow is very bright and then it dims, okay? And you see all these rings. And this was really, really impressive. To give you an idea, this telescope is new. It's been around, relatively new. It's been around since 2011. To give you an idea of how much better this telescope does compared to the predecessor, here I show you this picture of the same telescope, of the same object. This is called H.L.E.V.E.R, is in the constellation of Taurus. With taking the same object, the same wavelength, taken with older family of telescope and this new telescope. And you see the angular resolution improved by a factor of 10, and this is the size of the solar system as a reference. This is one of my preferred friend, my best friend. It's called MWC 758. It's another young star in the constellation of Taurus. It's slightly bigger than the Sun, and when you look at with Alma, you see the star at the center, surrounded by a little bit of dust, and that's what you see. Again, you don't see the star. And then there are these rings with this big crescent on one side, okay? And what you're looking at here is dust particles, and the scale, if you put the solar system on top, it looks like this. And what we think is that this structure and the fact that there is no dust in the center is because there are planets that are pushing away material and clearing up this feature. I can show many beautiful pictures of this young planetary disk. This is another friend of mine. Again, a beautiful ring. The color don't mean anything, as you should know, because you are part of an astronomy club. So okay, these are all monochromatic images taken at a wavelength of 1.3 millimeter, and then we use color just to make them look nicer. But the intensity is what matters, and you see the scale of the solar system. Again, big rings and gaps.
Dr. Isella.
Oh, yes.
We have a question. Is
Sure.
Alma affected at all by weather?
Yes, it is, because despite the fact you are at 5,000 meter elevation, there is still weather. It snows. There is what is called the Bolivian winter. So for a couple of months a year, you can actually get a significant amount of snow. And despite the fact that it's the driest place on Earth, and also even if it doesn't snow, there might, as you know, there are clouds above 5,000 meter elevation, and the water in the atmosphere. Well, there are two problems. One is the amount of water, which is like having a curtain. So it just absorbs. It's a semi-transparent curtain, and because we are looking at very dim objects, you don't want to lose any light. The other is that there is turbulence in the atmosphere. The atmosphere is not just a curtain, but is a moving curtain. And this turbulence spread out the light even at this wavelength and produce what in the optical is called seeing, for example, blurs essentially the images. So, and this is very sensitive to frequency. If you want to do observation at the shorter wavelength, they are much more sensitive to weather. If you do observation, let's say 300 micron, they are very sensitive to weather, even at 5,000 meter elevation. 3 millimeter is much less sensitive because the longer is the wavelength, the less is absorbed by the atmosphere. But yes, the only way to beat the weather is try to get as high as possible. Ideally, you want to go to space, but going to space is very expensive. Do you have any other question?
Not at this time.
Okay, so let me see. Okay, I'm almost done here. So this object here is peculiar because it's called Hydra in the Hydra Association. It's a small group of stars that are close to the sun. They are about 60 parsec away. For those who are not familiar with parsecs, it's about 200 light years away. And so actually, this is the nearest baby star to the sun, okay? Not the nearest star, it's Proxima, but Proxima is old, Proxima Centauri. This is the nearest young star to the sun, Hydra. And interesting enough, he has these rings, and if you put the solar system on top, these rings are at the location of some of the planets in our solar system. So this ring might be caused by some of the baby planets, and this system this star is the star itself is much redder and smaller than the sun, but in say billions of years, this could become a solar system similar to some extent to the sun. So myself and my collaborator used this new telescope in the last 5 years to take as many pictures as we could. And of these baby planetary systems, there is a gallery of them, and many more were taken by other people. We were the first one to use it in this way, and after us, a lot of other people used the telescope in this way. And what you see, all these objects are baby planetary system, and they all show this ring structure, right? Okay, so what do you do? I already told you. What do you do? Is we like taking picture, but we are also physicists, so it's not enough to take a picture, right? So what do you do with these pictures? Well, one thing you can do, you can compare this picture to this theoretical model that I show you, right? So again, the idea is that if you have a planet, the planet open up and create these big rings. You cannot see the planet itself because it's too dim, but you see these big rings, okay? And from the big rings, you can infer where the planet is and what is the mass of the planet. So we did that, and that's what we got here. Okay, this is a plot similar to the one I showed you before. The vertical axis is the planet mass, this time in Jupiter masses. So 10 to the 0 here is 1 Jupiter. See, this is Jupiter, Saturn, Uranus, Neptune, Venus, Mercury, Mars, and Earth, right, in this plot. And all these dots are exoplanet around all the stars. And the color is the different technique I told you before. So these orange dots here are these putative planets that we have not seen yet, but we believe they are there because we see these big rings, okay? As you can see, they have masses like Jupiter and Saturn, and they are pretty far away from the star, between 10 astronomical units, even 100 astronomical units. And there is an interesting family of planets up here. These planets are very massive, 10 to 15 times the mass of Jupiter, and they are extremely far away from the star. And it's just, it's a big question. I'm trying to understand, how can you form these big planets so far away? So it looks like this planet, the main idea before our observation was that some of these planets formed very close to the star and then moved out there after, due to some perturbation. But what we find is that you can actually form planet directly right there, right? Because the planet highlighted with these orange dots, these are very young. They didn't have time to go anywhere, right? So somehow nature finds a way to form giant planets very far away from the star. And this was a very new and surprising discovery. Okay, I want to finish very briefly talking about this green stuff. Because
Doctor,
yes,
can I interrupt you just for a minute? We got a couple of questions. The first one is, how much integration time is required to image an exoplanet?
An exoplanet? Well, okay, so we cannot ask a clarification. So exoplanet, the one around old star using radial velocity and transit techniques, that can take many hours, okay, because you need to follow the star of days or even years. The disk I'm showing you, how much time it takes to get each of these picture, if that was the question, perhaps. This one takes not much. With Alma, takes about half an hour of integration time, 1 hour to get each of these picture. So these are 20 pictures, so it took about 20 hours of integration times, which telescope time require much longer because there are calibrations and a lot of overheads.
Okay, give me just a second. I got to clarify something, and then I'll ask the next one.
Do you want me to go on, or I can wait?
Give me just a second.
Sure.
Okay. The next question is, what is the minimum size of accreted material that can become a small star versus becoming a gas giant?
Oh, yeah, that's a very good question.
Could that have, it's a two-parter. Could that have happened to Jupiter had it been 5 to 10 times its current size?
Yes. So what is when do we start calling them planets, start to calling them star? Okay, so as you can see in this plot, so these dots up here, they are 10 Jupiter mass. Okay, so the actual limit is not very well defined, but it's between 13 and 15 times the mass of Jupiter. And the reason is that if you have something that is more massive than, say, 15 Jupiter masses, then the central temperature is, due to the gravitational contraction, the temperature in the core of this planet becomes so hot that you can start to burn deuterium. Okay, deuterium is an isotope of hydrogen. Now, these are still not stars, because you burn a little bit of deuterium and then you're done. So these are not planets, they are not stars, they are called brown dwarf. If you want to really go to the star, then you need to be able to have a temperature you can burn hydrogen in the core. And then you need to go to maybe 50, 80 times the mass of Jupiter. So higher up, okay? But above 15 times the mass of Jupiter, then you should stop calling them planets. They're called brown dwarf. And we see a lot of brown dwarf as well, but that's another story, right? And there was this, what was the second part? Maybe I already answered.
The second part was about the size that it would take.
The size in terms of mass. When it's size, I mean mass, right? So because the size depends on the density. You can have something very big and very fluffy. Yeah, so what really matters is the mass. Yeah, so 10, 15 times the mass of Jupiter. Okay, let me try to finish here. So I was saying, so there are these, so if planets are up here, if you have any orange dot that is in this red square, this is where we can hope to take an optical telescope or an infrared telescope and actually trying to direct image the planets. These red dots are all planets that have been directly observed. As you can see, there are these two that have been observed with Alma. You see this large ring. This object is called PDS-70, has a large ring of dust. And indeed, using telescope, people have discovered, not me, but my collaborator have discovered two planets, very massive, between 5 and 10 times the mass of Jupiter, orbiting, one at 20 AU and the other at 30 AU inside this big ring. So these objects really validate our theories, where we see everything going on here. Planets form and push material away and open up this cavity. We even see dust around the planet itself. And this dust can be a disk around the planets. And we know that the moon of Jupiter, the Galilean moon, formed in a disk around Jupiter. So, and we are starting now to see even the dust around these planets, right? And so this is a work that I've done a couple of years ago, and was also picked up by general media like CNN. Okay, let me finish because I'm going long here. So I hope I gave you an idea of how we study formation of planets. The observation, radio wavelength observation, is not really radio, it's what we call microwave regime, so millimeter sun millimeter regime. Radio is more like centimeter and meter wavelength. Reveal planetary system in the making and tell when, there is a typo, sorry here, tell us when and where giant planets form. During the next several years, we study chemical composition of this material. I only talked to you about dust particles that emit lights, but we can also look at molecules and we can see what is the chemical composition of the material. Okay, and if I'm allowed to go on for another 2 minutes, I told you we discovered the planet we can infer the presence are as big as Jupiter and Saturn. So, and then you can say, well, but you start talking about formation of rocket planets, and now you only say something about Saturn and Jupiter. So, how about this planet? Is there any hope we can study formation of Earth? So, current telescope cannot tell you anything about formation of Earth. It's too small. It doesn't create the structure that we can see. Okay, but if you could build an even bigger telescope. So, before this talk, I was discussing with Doug about a little bit about the VLA. You may know in New Mexico, we have this beautiful array. It's called the Very Large Array that look at the sky at longer wavelength between gigahertz, 1 gigahertz, and less than that, actually, up to 40, 50 gigahertz. And so we have now a plan to, the VLA is old, is 40 years old, and we have the plan to replace the VLA. And when I say we, I mean the astronomical community, with a much bigger array where you have 10 times the number of antenna of the VLA, and this is called the next generation VLA. And this will consist of 263 antennas with baseline spaced by 10,000 kilometers, right? Because then you can use what we call very long baseline interferometer. You can put an antenna in Hawaii, antenna in Puerto Rico, and you can combine the signal, and you have a fantastic angular resolution. This is a simulation. This is my last slide. So what you will be able to do with this such beautiful telescope. So imagine you find a baby solar system, okay, where you have Jupiter at 3 astronomical units. We don't know exactly where Jupiter formed. We probably formed close to where it is now and move around a little bit. Let's say it formed at 3 astronomical units, so roughly where the asteroid belt is now. With this telescope, we will be able to take a picture like this, where we see Jupiter, we see material trapped at the Lagrangian point, what is our now Trojan satellites. But not only that, because Jupiter takes 11 years to go around the star, at 3U will take even less. So with that telescope, if you take a picture every, say, a few months apart, you will see this feature rotate around, right? We cannot do that now because if you find the planet 100 astronomical units, it takes several hundreds here to do one round around the star. So it essentially doesn't move. But if you can really zoom in, you can see this feature going around. So this is still a project led by the National Radio Astronomy Observatory. Unfortunately, these projects are very expensive. When I say expensive, I mean they cost more than $1 billion, again with the B. And so it takes a lot of time and a lot of politics to get them done. But we hope then in the next, say, 15 years to be able to build it. So maybe I'm going to come back in 20 years and give you a talk about images done with the next generation PLA. So with that, and I'll stop. I'll be happy to take any question you have. Thank you very much.
Okay, I don't see any additional questions. I'm going to go ahead and pass back to Doug.
Okay, well, thank you very much. That was a very interesting talk. I'm biased because I'm recently become very interested in radio astronomy, but that was great. Thank you very much for being our speaker this evening.
You're welcome.
All right, next up, we have a Members Minute with Chris and Treavor on the conjunction images.
Okay, this will be real quick, I think. So Chris and I decided we were going to get together and image the conjunction. Unfortunately, plans didn't quite pan out as to what we had intended. So basically, Chris got left doing the capture while I was out running a impromptu star party at another location. So we'll go ahead and show you what we have here. This is actually a little bit of the raw video footage that we captured. This is approximately a 2-minute video of the two planets. And I'm not going to run that through the entire thing, but you can actually see, you know, the seeing conditions, and you can see them moving around there a little bit based on that. Next up is the photon capturing apparatus, which is basically the telescope and the camera. We used Chris's Skywatcher SkyMax 180, which is a 180 millimeter aperture with a focal length of 2,700 millimeters. So that gives you the focal ratio of f/15. Then we had my Celestron Next Image 10 camera connected into the diagonal on the telescope in place of the eyepiece, and Chris had his Microsoft Surface Pro running the iCap software supplied by Celestron for controlling the camera. Then we ran the image or the video through Deep Sky Stacker. This is just the stacked image at this point. I haven't done anything other than stack it. Then we worked on the sharpness with the wavelets, so you can start to see those bands a little bit clearer. And then finally took it over into Photoshop and did some editing in Photoshop, and was able to brighten up Saturn while keeping Jupiter pretty much the same. And then you see two of the Jupiter moons in the image. That's just a laptop is what a Microsoft Surface Pro is. Just a very small tablet version. That was one of the questions that came in. And that's all I have, really. Thank you. Back to Doug.
Okay, Trevor, thank you for sharing that with us. Okay, next up, I have a members minute I'm going to call the M1 project. And M1 is the Crab Nebula supernova remnant in Taurus. It was seen by Chinese astronomers in 1054 AD. It's believed to be about 6,500 light years away. Contains an interesting pulsar, which is a rotating neutron star, pulsing at 30.2 pulses per second, which illuminates the nebula. And it's the brightest persistent gamma ray source in the sky, and it's also known as radio source Taurus A. So I'm going to show you I tried to take pictures, do some different types of imaging instead of just one style this time. I used a AT8RC rich accretion 8-inch f8 telescope with a field flattener, and I used the Bader narrowband filters for sulfur, hydrogen, oxygen, and I used a Sony ICX285 CCD based camera and a Micron MT9M034 CMOS based guide camera. Use a thin off-axis guider for this configuration. And I would have to say, if anybody trying to do something like this with the telescope of this type, you pretty much have to use an off-axis guider. I've tried using guide scopes, and they just simply do not work because, no matter what you do, the mirrors in these telescopes move around just a little bit. And it's enough that you really can't guide with them unless you use an off-axis guider. And the whole thing is remote control with the Raspberry Pi, so I can sit in my house and not out in the freezing weather, which with the telescope, running Indy, K-stars, and ECOS. And you've probably seen some of our presentations about that in the past, hopefully. Okay, so here's some results of M1. I've got some pictures of sulfur, hydrogen, oxygen. The sulfur on the left is going to be mapped to red, and hydrogen in the middle is going to be mapped to green, and the oxygen on the right is going to be mapped to blue. But what I like about this is you can look at these images and you can actually see where the different elements are in the supernova remnant. They're not all in the same place. I mean, sulfur is definitely in certain regions, and oxygen is more prevalent in other regions. Hydrogen does, go over pretty much the whole thing, but the sulfur and oxygen are definitely in different areas. Putting it all together, we get this image here. This is the combined image of the sulfur, hydrogen, oxygen with those mapped to those colors. I think it turned out pretty okay. A couple things about this. This is my oxygen images, and it's kind of, we all know, yeah, you need to have a night of good seeing and good transparency. But I think this is a pretty good illustration here. This is the exact same telescopes, exact same cameras, exact same everything, same number of images, 14 times 15 minutes on both of these. The one on the left was a night of poor seeing and poor transparency, and it was warmer, so I had more noise, and you can kind of see, hopefully, not sure how well this is going to come through on the YouTube channel, but the one on the left is noisier, and that's even with me trying to process out the noise. So it was noisier, it's not as good an image, and because it's warmer, poor seeing, poor transparency. The one on the right, it was actually pretty cold. I was actually able to get the sensor down very cold. I think below minus 20 degrees Celsius, probably minus 22, I think, degrees Celsius. And it's a much better image, as you can see. It had good transparency and good seeing on the night that I got the one on the right. Now, this is another thing, deconvolution. The image on the left is the same data, but it is not, it hasn't been put through deconvolution. The one on the right, I did use deconvolution. This was the PixInsight deconvolution. I actually like the one in AIP for Win a little better, deconvolution, but this is what I was processing this in. The PixInsight deconvolution is kind of a little bit of a stinker to learn how to use. It's kind of very touchy, but if you're patient and you keep working with it, eventually you can get some reasonable results. This shows the difference between not using deconvolution and using deconvolution. The one that the image on the right should appear more sharp to you, hopefully. Now, I also went out and I took some images as an LRGB image, or luminous red, green, and blue image, which is what we would normally see with just a color camera. It's the exact same telescope, exact same camera, exact same everything. The one on the left is an LRGB image, and the one on the right is my narrowband image. So you can see the difference between just going narrowband versus LRGB. And like I've said in the past, I mean, I like doing narrowband imaging because you can really see a lot more detail and structure with the narrowband. And believe it or not, as we speak, I'm actually running the telescope in the backyard on the same computer that I'm doing a presentation on, and I'm doing near-infrared imaging of the Crab Nebula. Maybe I'll be able to show that to you in the future. And that's it. So next, I would like to pass it to David with Star Party News.
David, you're good to go.
Okay. Hang on, I don't think oh, I did unmute. Was unmuted. Okay. Sorry about that, folks. All right, this is going to be equally. We had nothing in the recent past, so we have no reports to worry about. January 23rd, hot off the press, we have an event at Hack Winery. Sunset is at 5:52, twilight at 6:17. It's going to be a waxing moon, 75% lit. If clear, we should also see Orion among a few other things, so it could be a really good night. 5 more dates with Hack are currently under discussion, but nothing else. That's the one they wanted to get off real quick. Nothing is on the agenda yet. There is hope once we get past this wave, and as long as social distancing is observed, vaccinations coming out now, hopefully we can tepidly step back into the outreach arena. And with that, we've got a father alien talking to his son, and why alien abductions occur mainly at night. And the father looks at him and says, "It's 9 p.m. and you're now telling me you need a human for school tomorrow." That's all, folks. Back to you, Doug.
Okay, Doug, you have a go.
Okay, David, thank you for the Star Party News. I always enjoy your cartoons. That was a good one. Thank you. All right, so that's the end of our meeting. Our next meeting will be on February 12th, and we will have the Mars 2020 mission T-minus 6 days with Dr. German Martinez with the Lunar and Planetary Institute. So thank you for joining us tonight, and hope you can join us again next month. Have a good evening.